starts talking about the syllabus. So, my last name is pronounced Mizzou. The J is silent. So, just so you know, my office is 416E in Benton Hall, so it's just up one floor, and then if you go back through the glass doors, then I'm at the very back. The office hours right now I have listed as just by appointment, so we're a pretty small group, so I think we can do office hours by appointment if that works for everybody. That way it's a little bit more flexible. Let's see here. Couple more things I need to correct here. Okay, so the prerequisites here, I just wanted to make sure that everybody sort of has the requisite mathematics. So in our department, this would be Physics 3200 and 3231. So those cover just sort of the basics of the math. They used mathematics that's actually in Math 2000 and Math 2450, but in a physics setting. So the most important thing that we're going to need as far as a prerequisite goes is linear algebra, which was Math 2450. And so because it's so central to the course and so central to what we're going to talk about, I'm going to cover a lot of that this morning, and then or this afternoon, and I'm actually going to give you a handout of the mathematics that we'll use most of the time in the course. Okay, so the lectures, we're using Townsend's book. Does everybody have a copy of Townsend's book?
I would like more.
I have a keep at online. I don't know if you need a hard copy.
It helps to, well, I mean,
I will have it.
Okay.
Yeah, let's see.
You can, I think I found like the first edition online. I think it's the second edition that there's a little bit of difference, but not too much.
So I don't know if we need a hard, before we needed a hard copy because they had an open textbook, open test, and so we needed a textbook for the test, and so I don't know if we actually need a physical copy or.
If we just have something to read,
okay.
the access.
It would be useful to have a hard copy for the exams, because the exams will be open book, open
Oh,
book.
okay, okay,
Yeah.
okay.
It's an excellent textbook, and I chose it because I, in particular, really like the way that the author goes through the material. This pen doesn't work at all. Somebody can I borrow a pen?
Yeah, here.
Thanks.
I got plenty.
So if you could please sign in there, and then pass it back to this gentleman back here. So we're going to follow the text pretty closely, and I have approximately what we're going to talk about during the week for the 15 weeks of the course. So we'll cover linear algebra review this week. Then week 2 we'll start into where the book begins, which is the Stern-Gerlach experiments, and so on. So the textbook follows sort of closely what if you all are familiar with Richard Feynman and Richard Feynman's, he wrote a very famous set of lectures for the freshman course that he was teaching at Caltech back in 1964. But of course, it wasn't a freshman course at all. It turned into a graduate level course, but or really just an upper level undergraduate course. And he covered his third volume of the Feynman lectures is on quantum mechanics, and this book that we're using is really the first author to sort of follow the style and the topics in the order that Feynman followed them in the Feynman lectures. And I like it. I like it for a lot of reasons over the other books. There's a lot of other textbooks out there on quantum mechanics, but they all start with wave mechanics and differential equations, and I would prefer not to start with that approach because that doesn't have a whole lot to do with really quantum mechanics so much as it has to do with differential equations. But we'll get to the differential equations as we go, but we just won't get there for a little while. We're going to really focus on the core of the mechanics of quantum mechanics. So the homework, there's weekly homework, and they'll be posted to the Canvas site. And you should download them and work on them. They won't be graded, but I will post answers for you to help you through those problems. I'm not going to post the answers right away because one of the mistakes that many people make in physics, younger folks, people trying to learn it for the first time, is they'll read a problem, they won't know how to solve it, they'll look up a solution, read the solution, and then they'll think that they understand what the answer is, and that's not how it works. So if you don't struggle with the problem, if you don't struggle with trying to figure out how to answer it, then you probably haven't learned much. And that's certainly true for just reading solutions. So I encourage you to form some study groups and to get together with people in the class and to work out the problems and talk about the problems. Because if the exams are going to be based basically on the problems that you solved in the homeworks. So if you're comfortable approaching the homework problems and their solutions, then you shouldn't have any trouble on the exams.
So how many homework problems is it usually?
There will be one a week.
1 a week? Okay. And then when would the solutions be posted?
I can post them probably a week or two later.
Okay.
Okay. All right, I think that covers kind of the syllabus here. We will have 1 or 2 in-class midterm exams, and they'll be open book, open note, and then we'll have a final exam. So, and it will be the exams that constitute the grade in the course. So just make sure, again, that you can do the homework problems and that you're comfortable with them. Yes?
So when you say open book, open notes, that sort of implies if our homework is done, that we'll have reference to that.
Sure.
Okay.
You can use your homeworks, you can use anything. Yeah, I mean, I would encourage you to, stick to just your book and homework and notes as far as information sources. I think it's easy, there's a million quantum mechanics books out there, and you can easily get lost in all of them. So, and most of them don't have the approach that this textbook has. So, the Feynman lectures are, of course, excellent. So, if you want to read those along with reading the textbook, nobody says it quite like Feynman did, and they're really, really nice lectures. Okay, so let me hand out this. This is what I'm handing out now is a primer, basically for all of the mathematical techniques we're gonna use in the course, most of them anyway. And just to cover the basics. So if you get confused during the semester about, what kind of math you need or something, about what kind of mathematics you need to use, it should be in this primer that I've printed for you. Okay, so before we start going through some of the material on the primer, are there any questions?
Oh, actually, so this whole, the quiz thing,
There's no quizzes.
no business, okay.
Sorry, this must be, I'll have to update the syllabus and reprint it. I think, I used a syllabus from the course there as the template.
Mm.
Yeah, if you have any questions, please just email me if there's questions about the syllabus or anything. Okay. Well, let's do a little bit of linear algebra review. So, the mathematics that we use to describe classical physics are things like differential equations, right? I mean, Newton's laws are a set of differential equations, well, his second law. And we typically just solve a lot of differential equations in classical mechanics, the trajectory of the baseball, or all of those kinds of things. And let me give just some brief overview here of the difference. So in classical mechanics, the objective is to find the trajectory of every particle. Okay, so it could be something like a baseball, or the rotation of a crankshaft, or any, just anything like that, where you can follow, the motion of, I know this particle is moving around this way, and every particle on this rotating disk or whatever is moving in a particular fashion, then I can write down the position as a function of time. This is a solution to Newton's second law, F equals ma, and that's it. I mean, that's what you do in classical mechanics. You want to find the trajectory of particles. Okay, in quantum mechanics, it's much different. Okay, in quantum mechanics, we don't ask about the position as a function of time because it's not generally something of interest. and in fact, you know from the Heisenberg uncertainty principle that you can't actually measure accurately the position of a particle without then losing information about its momentum, okay? So some of the questions that you can ask in classical physics, you can ask what the position of a particle is and get it to infinite precision. It's not in principle impossible to do that, but it is in principle impossible to do that in quantum mechanics. So in quantum mechanics, we have a state. And we'll just denote it by, this is the Greek letter psi. Okay. And psi is psi is the state of the particle. It contains information about location and things like that. So, we can ask about psi as a function of x and psi as a function of x and t. Okay, so let's contrast the two, because in classical physics we have x, which is the position, and we have a parameter here that's time. Okay, so in classical physics, I might have, this might be the trajectory of a particle. Let's say this is x of t. And so if we tick off seconds here, I can tell you, where the particle is at every second. So t is the parameter that describes the position. Okay? But in quantum mechanics, we have the state function, psi, and the parameters for the state function are x and t. Okay, so x is only a parameter. In quantum mechanics. Okay, so you can think of x getting a demotion here. It's no longer as important as it used to be. It's only a parameter in the state function. Okay, and so what we're going to spend the semester doing is trying to figure out what these objects, what the state function is. So what is the state function? Okay, so that's our goal. Okay, so let me lead into why we need linear algebra. Okay, it's a linear combination of other state functions. Okay, and so we'll do things. We'll write things like the following. We might write that psi is equal to A1 phi 1 plus A2, phi 2 plus A3, phi 3, for example, where A1, A2, and A3 are complex numbers. And phi 1, phi 2, and phi 3 are what are called basis functions, so basis state functions. Okay? So now I've used two words from linear algebra. I've used the linear combination. So this is a linear combination because I'm not taking powers. There's no powers of my phi's, so it's linear. And I'm just summing them together, and I have some coefficients here that are complex numbers. And what we'll see is for example, what we want to do is we want to take a vector. This is a vector. We call it a state function in quantum mechanics, but it's just a vector. And it can be decomposed into a basis just like you've done in your linear algebra course. Okay, does that make sense, everybody?
So the A's are the coefficients and the phi's are like the X that you would use in your algebra, like X1, X2, X3.
Sure, yeah. I mean, if x1 and x2 and x3 are basis vectors, yeah.
Yes.
Okay, everybody good so far? Okay. So the other thing that we're going to learn as we go along here, I want to teach you the details of, how all of this stuff works. It's, the simple part of dealing with the linear algebra is just part of understanding quantum mechanics. To really understand what it means is going to take the larger portion of the semester here to go into a lot of the details. Okay. So let's just recap then. Let's look at just basic linear algebra. And the first thing I want to cover is, this is 2.1, vector spaces over R. Is everybody familiar with this notation? R is the real numbers, C is the complex numbers. Okay. Okay, so just by definition, it's a collection of objects, and here I can use this curly bracket notation. So I can say we'll use V1, V2, V3, and so on. So this can be finite or it can be infinite. Okay, so we're going to encounter both of these in quantum mechanics. We're going to start off with vector spaces that have finite dimensionality. And when I mean let's just leave it at that. Okay. We're going to cover some that have a finite dimensionality, and then we're going to also cover vector spaces that have infinite dimensionality. So to qualify as a vector space, so just following the mathematical definitions, we have to satisfy a vector space as a collection of objects that satisfy the following conditions. And there's a set of 7 conditions here. Okay, and these are just the typical conditions for anything that you want to, anything that is a vector space. So for it to be a vector space, if, let's say that all of these objects are in V, vector space V is a collection of these objects that are in the vector space. So if I take V1, any V, let's call it V sub I, say, plus V sub J, this is also in the vector space. Okay, so this means it's closed under addition. Okay, this is an important property because if we are going to, the space that we're going to talk about, the vector space is in general called Hilbert space in quantum mechanics. And if we want to find solutions to, say the state of an electron or something in our vector space, we don't want to be adding vectors that are in different spaces. Okay, that doesn't make any sense. We want vectors that are in the same space so that if I add them, I get another vector that's in the same vector space. So being closed under addition is an important property. And the second property is that if R is, so we're doing vector spaces over R first. So if R is in the reals, then R times any vector VI is also in V. Okay, so that means no matter how big I make my vector, no matter how long I make it, it's still in the vector space. And then property 3 here is that it's commutative. So if I take VI plus VJ, that's equal to VJ plus VI. Self-evident, but that's still, it's a property that we need. We need it to be associative. So that means VI plus VJ plus VK. If I associate the first two together, that's the same thing as VI plus VJ plus VK. Okay, and we need this is called scalar multiplication. If you're number 2. We need scalar multiplication to distribute. So that means that R, if I take a real number times VI plus VJ, that's the same thing as R VI plus R VJ. Okay? That's a property we'll use all the time. And then 6 and 7 here are also very important. One of them is that in a vector space, we have a null vector. So there exists a null vector. We can write it, as 0, such that VI plus, any vector VI plus 0 is equal to 0 plus V sub I. And then we have an additive inverse. So for every V sub I, there's a minus V sub I that I can add to it that gives me the null vector. Yes,
From this, it looks like it's just saying that the null vector has to be commutative. Is it, I may be missing an I for it, it says VI plus 0 equals 0 plus VI. Wouldn't that already follow from, rule 3?
let's see, does it follow from 3? I don't.
Well, the first part is new. I think you're talking about specifically the second half follows from 3. But
Yeah, I mean, you could say it follows from 3. I guess it's,
would it also be accurate to say that?
it's, this is just equal to V sub I.
Yeah.
Yeah, I think the important part is that like, there exists a zero vector. That's all that is a vector.
Yeah, I think that would, is what I mean, like, I think I would understand it more as like VI plus the null vector is VI, I guess.
Yeah, I mean, don't get too caught up in my numbering here because, you go to different linear algebra books, you'll find, you won't, sometimes it'll be 5 or, 7. I was being just more.
I feel like I asked the same question in linear algebra many years ago.
Yeah.
That took me out.
All right. Okay, so this is just a basic vector space. And they're useful things, but in quantum mechanics, we will add a little bit more structure to the vector space. And we'll do this by introducing an inner product. Okay, so that this is just the definition of a vector space. A bare vector space doesn't have any further structure. But if you want to put extra structure on it, you can, and this is the one thing that we will do is the inner product. And so we can denote the inner product as, say, V dot W with a dot. So this is the dot product. Okay. So I'm writing everything in a form that you should all be familiar with. But I warn you that once we're done with our linear algebra review, I'm going to change notation on you. Okay, and I'm doing that. I'll do that because the notation that you typically learn in linear algebra is not so convenient for us. So, but I want you to see it, and then I'll cover it again in the new notation. Okay, so the first thing we want to do is just define this. We want to define this inner product. We'll call it a dot product here. We'll call it just an inner product in quantum mechanics. But you are all familiar with this. So V dot W would be V1 W1 plus V2 W2 plus say V3 W3 for vectors in R3, for example. Now, the properties that we really like in the inner product one thing that's really important is that when I dot a vector into itself, it's positive. I don't want to get anything negative. It can be 0, but I certainly don't want to get anything negative. So we want positivity. So V, if I take a vector and dot it with itself, that this number be greater than or equal to 0. So it's a positive semi-definite, but I want it to be a positive number. Certainly do not want it to be negative.
So this is a bit different from the normal dot product then, if I remember correctly? because I believe the original has like I believe it says the sign.
Oh, we're getting there.
Yeah, which
Yeah.
can't possibly-
if, this is with itself,
Oh, with itself, never mind.
not, yeah, this dot product can be negative,
Okay, yeah,
but I want positivity of the vector with itself.
yeah, no, I didn't see it with itself.
Yeah, sorry, I should make that clear. So that's one property that we have to have, and then the second that we really want is the Schwartz inequality. Which says that the V dot
New
W,
term, but not a new thing, just the dot product is less than. That's what this means, right?
less than or equal to the magnitude of V times the magnitude of W. Okay, so these are two different vectors. Okay, are there any questions so far?
I assume one would apply to anything that is a scalar, either of the original, like if you dot spin with the scalar itself.
Sorry, say that again?
If, you dot spin with the scalar itself, it also has to be positive, I would guess, too, right?
Well, a scalar is not a vector, so it can't participate in the dot product, in the inner product.
I mean, like if you had, a vector that was in the same direction, but with a different size.
Yes, that would be positive. Yeah. Other questions? Okay. So let's talk about basis sets. This is very, very important. So, in general, a vector in a vector space V can be decomposed into a set of basis vectors E1, E2, and so on. And this set can be, again, finite or infinite. So we can decompose any vector into a set of basis vectors, so I can write V is equal to A1, E1 plus A2 times E2 plus, and so on, where the AI are real numbers. And the basis set E1 it's said to span the vector space V. Okay, now, what we're going to do, we can write, we can change bases at will, and we'll do this a lot because it's very convenient to solve problems. And so the same vector space can have many different bases. So we could have another basis that's E1 prime, E2 prime, and so on, and I can still write the same vector V in terms of it. So in this case, we would write A1 prime, E1 prime, A2 prime, E2 prime, and so on. So we can decompose the same vector in terms of other bases. So what we'll do is we'll be able to, we'll switch bases depending on you know, what problems we're trying to solve. Now let me introduce you to some more notation. There's quite a bit of notation that we're going to use throughout the semester. So
The base is necessarily equal to the number of coordinates in the space. Like if you had like a three-dimensional system, would there be like E1, E2, and E3, or would you have more?
no, that's right. If you know, if you have three-dimensional space, you would just have E1, E2, and E3. But we, you know, we'll have spaces of various dimensions. So yeah, we'll have to keep that in mind. So it's, when you choose bases, though, it's useful to choose bases that are called orthonormal.
So like
Okay.
X, Y, Z.
Yeah, so that in particular, so the magnitude of a vector is defined in terms of the inner product. So if I want to calculate the magnitude of this vector, so this is just a number, this is equal to just V dot V to the 1/2 power, right? I just this, you can sometimes people write this as V squared or something, but so that's just this is just, once you take the magnitude, that's just a number, okay? But so one of the reasons why we really want an inner product is because we want to be able to define the length of our vectors, and we want our basis vectors to satisfy the following. We want well, let's see, so E sub I want to take the magnitude of E sub I want that to be 1. So I want the magnitude of my basis vectors to be 1. And then we want E sub I dotted with E sub J to be, this is the Kronecker delta Ij. Okay, so the Kronecker delta is it's 0 for I not equal to J, and it's 1 for I equal to J. Okay, so this is just a symbol called the Kronecker delta, and it takes the value 0 when I is not equal to J, and it takes the value 1 when I is equal to J. And so if I take the inner product of two vectors EI and EJ, if they're different, I want them to be perpendicular. So this is a relationship that I want. Okay, so let's just do a quick, example. So in R3, let's let our vector space V just equal R3. Okay, so now I can set E1 to be 1, 0, 0, E2 to be 0, 1, 0, and E3 to be 0, 0, 0, 1, right? This is just what you all know from your intro. Or from your linear algebra courses. Okay, and then I can draw a vector in here. So let's say I draw this vector V, and then I can decompose it into its 3 components. Okay, so this would be this distance here. That would be, so if we write V is equal to V1 E1 plus V2 E2 plus V3 E3, then this will be V3, this distance here will be the projection along the E2 axis, so that's V2, and this distance would be V1. Okay? All right, that's you're all very familiar with this, and I'm doing it because when we start doing things in quantum mechanics, you can think, you'll be able to think of this as psi, and these things as like phi 1, phi 2, and phi 3, okay? That I wrote down before. They're not going, this picture that we have in 3 space, it's a very useful picture, you can really think of it this way, and it's fine. But when you go to take inner products, it's not as simple as doing a dot product. I mean, initially it will be simple like this, but some of our inner products are going to be integrals and things like that. So, but always go back to this picture that you already have in your head. And this is how I want you to think of these things. So, this might be the state of the electron, and it's built up out of, different components, these different basis states of the system. Okay. All right, so let's talk about linear independence, because that's important. I'll just do this by example here. So if A1, let's see here. If AV plus BW, if I'm taking 2 vectors, equals the null vector, implies that A equals B equals 0. Then V and W are linearly independent. Okay, this confuses a lot of folks, so let's just quickly think it through. So what we're saying is, if this relation that I write down, if this relation implies that A equals B equals 0, then they're linearly independent. Because what that's telling you is that there's no component of V along any component of W, because I can write the zero vector. That's the other importance of the zero vector. Okay, and this is important because we obviously want linearly, what we'll see is that if I have, let's do some examples of what's independent and not independent. So in two space, if this is V and this is W, these things are independent. Okay, but if I have W, if I have any component of V at all along W, then that means I can decompose V into some piece that's along W. These are not linearly independent. Okay, that's all it means, and it's so it's very, there's a picture that says it very, very easily. But this is the mathematically correct statement, and it hinges on this use of the zero vector, and that this relation implies A equals B equals 0. But as long as you have the physical picture here, then you're fine. Okay, good so far. All right. So one of the issues a lot of students have when they first take quantum mechanics is just the amount of notation that is thrown at you. So I know it's a lot. That's why I put all of the notation that I'm covering now is also in the handout. So you can always go back and refer to it during the semester. Okay. So now let's, we want to be able to write vectors in various ways that are useful to us. So, and to doing that, we'll often use matrix notation. That's just a very convenient way, because also when we transform vectors, as you know from linear algebra, you use a lot of matrices to transform them. So let's look at ways of writing vectors. And I'm going to be really particular about it here, because I want you to really think about the notation that we use, because when we go from real vector spaces to complex vector spaces over the complex numbers, then the notation becomes extremely important, and how you manipulate the vectors becomes really important. So let's look at just real, again, we're still doing real vectors. So so if I write V, let's write it as, let's pick something, V1, let's see, I'm using, all right, so I already, when I write the basis vectors, I meant to use hats.
The hat means it's normal, right?
Right. Exactly, yeah, that's typically what it means. So if I write a vector in terms of these orthonormal basis vectors, so we have EI dotted with EJ is equal to delta IJ, okay? So I have an orthonormal set of vectors that I'm decomposing into, and I write the vector like this. I can write it in terms of a column vector. So V1, V2, down to Vn. Okay, that's a column vector. Okay, and the transpose let's define the transpose. We'll write that as V with a capital T here, and I'm gonna write it in a funky way.
Just horizontal, isn't that, you just turn it?
In this case, yeah.
Okay, so I don't know if if you've ever seen the things written this way, but,
That's actually the way, I did my calculus class, except instead of having like the really long parenthesis on the top, we had like.
The little short parentheses on the sides.
yeah, okay, but, I think this will, what I like about writing it this way is the following. I can write the magnitude of V squared then as V transpose dotted into V. Okay? Because now we're doing a matrix multiplication. So I go across and down. All right, does everybody see that?
And now these two notations aren't showing the basis anymore, so does that mean that you have to show the basis before writing them this way, or you're assuming that the basis are, something?
Well, we would have to, yeah, I mean, you assume that you have this basis, so that your basis vectors then, so E1 would be 1, 0, 0.
Yeah.
And E1 transpose then would be 1, 0. Yeah. Cool with that? Okay. Okay, so.
And the transpose is just notation here, it's not like an actual matrix transpose, we're just relating it to a matrix transpose.
It is the matrix transpose, but this
It's
is,
the same vector, they're equivalent vectors.
well, it is the matrix transpose. This is just not a square matrix, right? It's
Yeah,
a 1 by n matrix.
Yeah, then because of that, it means they're really technically the same vector, it's just.
They are for real. I mean, they live in different spaces in a way, so.
They look like the same vector, but they're technically not. I think it's more accurate.
Right, I mean, they represent the same vector, but the transpose is actually a different, it's a different object.
So I couldn't add, V transpose to V.
Correct.
That's interesting, because I always thought that the vertical, notation and the horizontal notation were just different ways of showing.
They are, but they are different ways of showing it, but they're not
It
the
would be
same.
bad to mix the notations, is what you're saying.
No, so when we, just hold on for a minute, because once we go from real to complex, then this will get interesting. And that's the whole reason why I want to show you this way. Okay. All right, so I have a couple of examples that I worked out in the notes here, and I don't want to write all of those down, but just with you can just take a look at those examples if you want to plug in real numbers for a small vector space or a small dimensional vector space. Okay, so let's see, where are we? All right, let's keep going. Let's do everybody comfortable with complex numbers? Everybody's seen them?
Yeah, we also have to have them in mechanics as well, for some of the proofs, so.
Okay. Okay, well, so let's just, a quick review. So, a complex number Z is written Z equals X plus I. This is like the way that physicists write this all the time, where X and Y are real. I squared is equal to minus one. Okay, now, I won't be able to tell you, in quantum mechanics, we'll talk about this a little bit later, but complex numbers are like they're forced on you in quantum mechanics. You can't do quantum mechanics without having complex numbers. So it's just part of the mathematics that is just forced on you. And so we have to deal with things like complex numbers in front of our vectors. Let's cover some of the basics here. So the conjugate, complex conjugate, of Z is denoted Z star, and Z star is equal to X minus IY. So you just change the sign of the I. Okay, and that means that magnitude of Z squared is Z star times Z, and that's just X squared plus Y squared. Okay, so complex numbers have this property that if you take the complex conjugate and multiply it by the number itself, you always get a positive number. Okay, so now we will study vector spaces over the complex numbers.
And the Z star, right?
This is a star, yes. Okay, so let's write down a vector in a complex space. So suppose W is a complex vector space. With a basis W1, W2, up to Wn. So any vector then we can write any vector in general. W is C1 W1 plus C2 W2 plus Cn Wn. Okay, where each Ci is now a complex number. Okay. All right, so now, when we want to, look at this board. We don't just want, we demand it. We want it to satisfy that the inner product here is also greater than or equal to 0. Let me write this. If you go back in your notes, just take this dot out here, because once I write it in this, once I write V transpose V, I don't need the dot, because this is now matrix multiplication. Okay, so, we still want this to be, you know, a property of our space. So now what happens? If we write W,
Does this mean y has to be less than x?
sorry?
Does this mean y has to be less than x? Because, it has to stay positive, so y has to be a smaller, or at least an average than x for it to stay positive when you square I.
No. If I work this out, this is x plus iy times x minus iy. So that's x squared, and then I'll have plus ixy minus ixy, they cancel. And then when I multiply these two together, I'll have I times minus I, but that's minus I squared. But I squared is minus 1, so that's plus y squared.
So we're adjusting it by adding a minus sign to one of the, we're adding a minus sign to cancel out the I.
No, we make this definition. There's a star here. This is the conjugate. So when we take the conjugate of a complex number, it's defined as by changing the sign of the I. And then so when we multiply z star z, when we multiply this out, I just use the normal, you know, expansion of this product, and then I get two terms will knock each other out. And then I'll just be left with x squared plus y squared. That make sense?
Okay, and so this is, in order to ensure that we have we always have a positive dot product or inner product.
Well, in a minute, yeah, almost. So now if we write W, if we want to represent it in this column vector format, I'll write C1, C2, down to Cn, okay? So the big difference is, and this is the thing that I want you to pay attention to, you'll be doing this very, very soon. As soon as you write W transpose, when you write the transpose of a complex vector, you have to take the complex conjugate of every number in there. Okay, and that's so when you write W transpose W, that you get the magnitude of C1 squared plus the magnitude of C2 squared plus the magnitude of Cn squared. Okay, this ensures positivity because these C's are all complex numbers, and so when I take the magnitude squared, I always get a positive number. Okay, so these are two very important types of vectors that we're going to work with, and you're going to be flipping from W to W transpose a lot. Remember always to conjugate. Okay? That's a huge thing. I can't tell you how many people get stuck on this. They
And I guess
conjugate whenever you do the transpose.
it's interesting is we were allowed to change the, basically flip the coefficient, the complex coefficient. I guess maybe there might be some reason we're allowed to do that, but it seems like.
Well, yeah, because because we want the property in our vector space. Like I want a
Oh,
vector
that's right,
space.
we can define the dot product to whatever we want in the vector space, right? As long as it satisfies the properties.
Well, yeah, I just did.
Yes, okay. Yeah, I was thinking of like one where it's like, oh, you can't change it, like, no, it's like basically, this is what we're calling the dot product, because this is what satisfies what we get.
Well, yeah, but we need that, right? We want that. If we want our vectors to make sense, if we don't want them to be negative, if we don't want the magnitude squared of our vectors to be negative, in certain cases, then we have to demand that this is what we just have to do to the coefficients to make it positive. Okay, so I think we'll go ahead and stop there for the day, but just keep this in mind. We'll go through this again in different notation. Shoot soon, if not the end of this week, maybe beginning of next week.
So is there homework for this week or no?
Yeah, it should be available.
Okay,